Welcome back, Chemistry 30. This is EQ1.3, Understanding and Working with Equilibrium Constants. So in EQ1.2, we saw what the equilibrium constant was, how it's calculated, basically a ratio of products to reactants. So here we're going to relate the size or magnitude of an equilibrium constant to the amounts of reactants and products present in an equilibrium mixture. So it is valuable to understand that with the magnitude, or whenever you see the word magnitude, that really means size, of an equilibrium constant, what it actually means. What does it tell us about how much reactants and products we have? For example, consider the experimental data for the reaction of carbon monoxide gas and chlorine gas to form phosgene, COCl2, a toxic gas used in the manufacture of certain polymers and insecticides. So here's the reaction right here. And if we were to figure out the Kc, so product over reactant, CO, Cl2, Cl2, and of course, coefficient becomes the exponent, we get that, which is a really big number, 4.56 times 10 to the 9. That decimal's 9 places to the right. It's a big one. So for the Kc to be so large, the numerator must be much larger than the denominator. And of course the numerator, what's on the numerator? COCl2. So the product, that's what's on top. So we must have a big number there over top of small numbers, which are represented by the reactants. So what we say here is that the equilibrium lies to the right. So there's much more of this made and a lot of that being used up. So we say it lies to the right. The reaction favors going to the right, and of course what's on the right? The product side. If the Kc value was small, so in between 0 and 1, a fraction, so you of course know that the bottom number would be bigger than the top. Bigger denominator means more reactants compared to products. So here's a schematic on the bottom here. So if K is much bigger than 1, that means in terms of mathematically speaking, the numerator is bigger than the denominator. And of course, in the numerator, we have products. And on the denominator, we have reactants. You can think of it as big amount of products over small number of reactants. And of course, if K is less than 1, but bigger than 0, our denominator is much bigger than the numerator. And we say it lies to the left. So where is the larger amount? To the left. Where is the larger amount? To the right. All right, so that's kind of the terminology that we use to describe the magnitude of KEQ and in which way the equilibrium lies. Which way is the reaction favoring? Okay, if you look at the next page, we'll look at some more of this. The following diagram represents 3 different systems at equilibrium, all in the same size containers. Without doing any calculations, rank the systems in order of increasing Kc. And of course, Kc, we know, is the ratio of products to reactants. So if we see large amount of products compared to reactants, that tells us we're going to get a bigger result here, right? Because in math, a large numerator divided by a smaller denominator gives a big number. Then if the volume of each of these containers is 1 liter, and if each sphere is 0.10 moles, actually figure out what the Kc is. All right, so there's a little problem with this one in that we're talking about colors here, red, blue, green, yellow, and unfortunately I photocopied it in black and white. So I'm going to give you a little hint in terms of which sphere is what gas sphere is which. So red, blue, red, blue, blue, red. This one's blue, this one's red, this one's blue. So if we count them up here, 1, 2, 3, 4. So there's 4 reds, and 1, 2, 3, 4, 5. I think 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I thought I had 6 blues here. 1, 2. Oh, I forgot to label this one. This one's a blue. 1, 2, 3, 4, 5, 6. 6 blues. There we go. Over here, green, green, green. Green, 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 and 1 yellow. So 1, 2, 3, 4, 5, 6, 7, 8. So 9 green and 1 yellow. Here we have red, red, blue, red, 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 blue, red, red. So in total, let's see here, 2 blue and 8 reds. So if you were just to take a quick look in terms of A from least, so KEQ, from least largest to most largest. Okay, not really grammatically correct there. So from least to most. The one that had the smaller number, the smaller KC, remember we calculated by doing products of reactants. Products of reactants, products of reactants, products of reactants, 6 over 4, 1 over 9, 8 over 2. So of course you can see that our smallest one must be this one right here. Because we're going to have 1 divided by 9. If you look at here next, 8 divided by 2 is 4. 6 divided by 4, 1.5. So that tells us, oh, that one must be next. And then that one. All right. Now, for part B, to actually figure out the KEQ, we have to look back to Physical Science 20 to look at how you figure out molar concentration. So here you have solute, which is in moles, divided by solution, which is in liters. So moles per liter. So if we look at this, so first of all, so number 1 here, we're looking at red in equilibrium with blue. So we're doing this first one, okay? Now if we take a look here, each of these spheres we're told is 0.1 moles. And let's see how many we have here. So for red, we have 4 of those spheres, and each one is 0.10 moles. So that's going to give us 0.4 moles overall. For blue, we have 6 spheres, and if each of those spheres represents 0.1 moles like we were told, that's going to give us 0.06 moles. And I could do that for all of them here. I might as well. If I'm looking at number 2 here, green to yellow. So green, we have 9 of them. And each sphere, we're told, again, is 1 mole, or sorry, 0.1 mole. And yellow, of course, you can see what's going to happen here. All right, if you look at 3 here, kind of running out of room here, it's blue going to red. So if we look at blue, we have 2 spheres, each one's 0.10 moles, so it's going to be 0.20 moles. And red, we have 8 spheres, so that's going to give us 0.80 moles. All right, so we have the preamble. So to figure out C now, the concentration, now it's easy because, hey, it's in terms of 1 liter. So if I'm looking at red, the molar concentration of red, number of moles divided by volume, 0.40 moles over 1 liter. So it's 0.40 moles per liter, or back in physical science, we call it big M for molar. Blue, C equals number of moles over volume, 0.6 moles over 1 liter, 0.0 moles. And then, hey, we can do this here. We can make this quick because we know we're just going to be dividing by 1. So molar, 0.1 molar. Then over here, blue is going to be 0.2 divided by 1, which is 0.2 molar. And red is 0.8. We don't have to show all the work here. It's the same process. And the volume is easy. It's 1. So this first one, KEQ, is equal to the molar concentration of products over reactants. Products over reactants. So B is 0.6, R is 0.4, so we got 1.5. If I'm doing this one, the equilibrium expression, products over reactants. So product is 0.1 over reactants 0.9. So that gives me a KEQ value of that. And then the last one here, whoops, should have moved up my paper here. So 0.1 over 0.9. Product B 0.6 over reactant 0.4, so you can see how that works. So product is red over reactant is B. Red is 0.8. Reactant is 0.2. So 0.40. All right, so that's how you figure out the equilibrium constant. We use molar concentrations, and then we can kind of see the relationship here. So this one we'd have products favored, reactants favored, and products favored, because KEQ is bigger than 1 in both of these, and it's less than 1 in this one, but bigger than 0. All right, you should be able to do the assignment. See you again.